for about 10 years, where she established and led Warwick Fire, a multidisciplinary research lab for fundamental and applied research in fire explosions and other safety-related reactive and non-reactive flows. She had many positions before Computational Fluid Dynamics Limited, British Gas, South Bank University and Kingston University London, where she was full professor since 2000 and head of the research for engineering in the period 1999 till 2012. At the moment, Jennifer is Fellow of the Institution of Mechanical Engineers, Vice Chair of IAFSS, and Chair of the IAFSS Research Subcommittee. She is Steering Committee member of the British section of the Combustion Institute, UK Explosion Liaison Group, member and sub-task leader for the European Hydrogen Safety Panel. She established by the Clean Hydrogen Joint Undertaking of the European Commission, and also Jennifer currently sits on the editorial board of the Proceedings of the Combustion Institute. Her research covers a wide range of topics, including fire dynamics, flame spread, salt fires, battery fires, blazing behavior in fires and gas explosions. But her expertise is primarily in CFD and in modeling of fire and explosions. She has applied fundamental combustion science to study a wide range of fire scenarios, including liquid cool and gas burner fires, single and multi-phase jet flames. Please join me in welcoming Jennifer. Jennifer, we're very curious to what you will teach us today.
Thank you, Bart, for the introduction. And I would like to start also by thanking Margaret and McManley for nominating me to give this plenary speech, and for the program committee for selecting me. And what I would like to do is to share with you and my journey in fire modeling, especially some recent work we have done. But I will also, in the past, mention examples about some excellent work in the wider IAFSS community. So this is not a literature review, and go along with my thoughts and along my thinking. If I couldn't find my own work, I found other people's work, and to illustrate what I wanted to say. I divide my talk into really just three themes, and which underpinning by my thinking that we need to do fundamental research, and for fire modeling, we need to do development and validation, and then apply it to different scenarios and to engineering problems. And I also think that as a community, while we are all in many countries, especially in the West, we are struggling to get more funding for fire research. And it's time we need to look at the emerging technologies. They bring challenges as well as opportunities. So I will start with my first topic, which is about physics-based submodels. And you all know that for fires, we got turbulence, we got combustion, and we got soot and radiation. So I wouldn't talk about turbulence today, but I will start with combustion. And in front of you, the graph you can see, it's a 2011 paper written by Ying-Wang and his colleagues. The reason I brought this up is that mixed bend is a simple model which they developed in the beginning of fire form, when it was modified and created out of the broad frame of open form. So this is a simple combustion model. I want to bring up to show that when they developed this in their papers, they did something fundamental first to check the energy conservation of the model and its implementation. So that's represented here by the entropy flow rate and checking it through the computational domain, and which to me is very important because it's the fundamental sense, getting the fundamental correct, the energy balance and the sort of things, before we talk about reactions and the flow and the fire interaction with the buildings, with walls, etc. As to my own group, and during a period between 2010 and 2014, we engaged extensively on looking for another combustion model, And my group previously used the flame-based combustion model, and we also used the hybrid approach to look at partial premix combustion and in backdraft using FDS. And where we use the flame index approach with the FlameNet, and for the combustion, for the and then the more simplified model switching to when it's diffusion flame. But what we later felt like that for fire, we needed something even more faster. So we looked at the EDC, and what you see in front of you is the modified EDC form, and which my group finally produced. And that removed the tuning coefficients. As you can see, we have two constants there, 0.5 and 0.75 on the left. And we still follow the Magnussen's cascading concept, but we did some modifications and to impose, to use the subgrid quantities, and rather than the previous extension of EDC to LES, where people just directly used the turbulent quantities. And the reason for that, the consequence of doing that, as you can see, this is the EDC which people just made a straightforward extension from the runs-based EDC to the LES context. So you can see that the file, the profile in front of you, it's really lifted away from the flame base, where the fuel comes. And if you tell me this is a jet file, that's more possible because most jet files are lifted. But for poor files, this is unphysical. The reason for that happening is those extensions, it calculated the combustion rate from the turbulence quantities, the global values, while at the flame base, those are close to zero. So you wouldn't get a combustion rate there. And so with our modification, which I don't have time to go into details, and the flame is at the bottom, so they are now anchored and to the flame base. And we also compared, we did validations and compared with Bess Wickerman's early paper, the methanol profiles, the famous methanol profiles, which many of us have used. So we are getting reasonably good agreement. We don't get a perfect agreement. In fire modeling, it's challenging to get a perfect agreement. I would only say that we got a reasonably good agreement. And I would also like to mention some, many of you probably attended the MaxCFP workshop before the conference, which is an excellent initiative, and to bring modelers together and to look at the fundamental side of the modeling approaches, and from comprehensive experimental databases, and the modelers can better validate as well as improve their models. So on the left there, it's an example I took out from the 2021 workshop, and which was published, the proceeding was published. And what we could see there is, and reasonably good agreement are obtained for the temperature, and for the temperature on the left in the top. But in terms of the root mean square temperature, I think we got more variations and more discrepancies. And less so for the velocities, which is down there. And sorry, I forgot I have this more powerful technology. So yeah, for this temperature here, mean temperature, reasonably good agreement, but fluctuations and the root mean square, I think we got more discrepancies. Similarly for the velocities down there. And on the right hand here, and these are our contributions to the 2021 workshop. And this one is a slightly bigger file. It's a 1 diameter, and this 1 diameter methanol file. And so we compared the temperature. Obviously, there are many, many slots, different heights, and the center line, I just took out one of them to put it here. And this is about 21 centimeter height. So the temperature is reasonably good, but the root mean square quantities comparison with experiments, they are, I would think it's quite big discrepancies, and unfortunately we didn't have time to look at it. And because one thing I found challenging with MaxCFP is it's when we have different projects and we are putting time to do it, and once we solve problem, it's really difficult to find the time to see how can we change the model and to do it better, because it's not directly related to any projects which we have at that time. And another work which we did is suit. And it's really important. And we listened to the talk of Professor Consalvi's student yesterday. And in fire, the radiation heat transfer and gas contribution is only part of it, and the suit play a dominant role. And traditionally, the file community, we either use simple correlations or we use Lindstedt two equation model, and which we used as well in the beginning. But I was motivated to try to develop our own suit model. And what we did was, along with the modification of the EDC, and we also developed a suit model along the same style of thinking. And, but that's in the first paper, 2014 paper. But what we found with that, in that one, we made an assumption that the sucrose oxidation is a constant. So later, we re-looked it, and we used the partial stirred reactor concept and to modify that soot model. And the soot oxidation now is computed rather than assuming to be a constant. So we are getting some improvement there in terms of comparison with the experimental data. And I'm also hoping to pick up the suit model more, especially yesterday, and we saw more data coming out, the bender, and with a comprehensive set of PIV velocities, temperatures, as well as the early measurement of suit. So I was excited about that and looking forward to participate in the next MaxCFP and to look at that case. And another thing we did, we also spent the time looking at the radiation. And many of you know the green gas assumption, the constants, assuming a constant. And some of you may also use the weighted sum of green gas models. And it's important to note that there are many different formulations of WSGG in the literature. And they are banded models. They are also gray models. And by gray models, is what I mean is wave band is not considered. While the band models, they consider the band, but they are not like the detailed radiation model. And they would consider regions of band. So they can be 5 bands and 3 bands, because to do the radiation, considering the full spectrum, it's extremely expensive, which doesn't really pay off, as I said in the beginning, and for file simulations, because the suit contribution is more significant. So we looked at the different wideband WSGG models, and the interesting the message I wanted to give and on this plot is, for file simulations, in most cases, just using the Gray-Smith model, which is this one. It's the simplest one, the gray one, and it's computationally most efficient. Yes, it's good. Using the more detailed, computationally more expensive banded model of Smith himself, or Castle, or Johnson, and doesn't necessarily improve your results that much. And this is the work I mentioned of Professor Consalvi and his students. And they did some interesting work. This is a really fundamental study comparing radiation calculations, simple models, and with a very detailed model. I forgot what model called. It's really detailed. It's highly banded with many continuous spectrum of the radiation waves. But the important message that we're trying to give us is that, and the importance of turbulence. TSI stands for turbulence and soot interaction. So whether this is included and it affects the detailed calculation of soot volume fraction significantly. So I just wanted to highlight this, and TSI is important and it affects the soot calculation. In our simple soot model, we didn't consider this, and it's a point for those interested to think. Now I will move to the applications, and as Bart mentioned, we worked on a number of applications. I will start with the flame spread. And this is the flame spread and over PMMA, and which is a combustible and material, quite often used in experiments because it's simple. And so we compared the pyrolysis and the flame heights and with the experiments as well as the flame spread rate and the total heat flux. I wouldn't say that we have any invention in this. Basically, this calculation was done just using the modified EDC and the soot model and the radiation, which we investigated earlier. And there was some special treatment near the wall. And otherwise, it's just an approach to model flame spread. And then more recently, I got interested in flame spread over solid liquid fuels, and especially alcohol, and which is a low flash point, and we became particularly interested in the spread phenomena, and very close to the flash temperature of the fuel. So one paper already came out, and that one was very much inspired by Miller and Rose's paper in 1998. The reason we picked that paper is there are many papers about flame spread over liquid fuels, alcohol pools, and however, the information, sometimes the conclusion and the discussion, it's contradictory, and it's not clear among the papers. We found this Miller paper to be most comprehensive and with some solid measurements in it. So we looked at two cases, and one case, the above is the 290 K, that's below the flash temperature. So that we have a pulsating flame spread. So because of the fuel temperature is below its flash point, and what we are saying is that, and the flame moves and then stops and then move again. That's because the fuel temperature is below its flash point. It needs to be warmed up and to produce the flammable mixture in front of the flame and for the combustion to start again. So we got that pulsating mode. But when the temperature is higher, and it's a uniform spread. It's a uniform spread because there's always combustible material, a flammable mixture formed in front of the flame and ready to join the combustion. We got a uniform spread. And the boundary between that, between pulsating and uniform, is only about 1 degree. And within that 1 degree centigrade. So this is direct numerical simulation using OpenFOAM. And what we did is we solved the solid region, liquid fuel region, as well as the flame, and we couple them dynamically. But in the solid region, we tried to speed up solid region just incompressible, and then you got the reactive. We use the reactive form for this, and to do the flame dynamics, and so that's the comparison of the flame front position and with experiments. So we can see, and roughly we are in line with experiments, and that's illustrating what's happening in the front. And also, importantly, those doing experiments, it would be very nice if somebody tried to look at the substrate flow and to get some PIV data for that. I've been trying to talk to several people to do this, but nobody seems to be taking my suggestion up. And it probably would be expensive to do. Somebody told me it's really difficult to get the flow, the circles, recirculation zones in the liquid in the liquid region, and for model validation. And we saw it in the model, but experimentally people haven't produced those kind of data. And then moving to mechanically ventilated files. And this just some, I think I will skip quickly. And it's just some simple calculation, which my postdoctor did some years ago. And it's more importantly, I think, in the mechanical ventilated file, our chair, but and his researchers have done a lot of work and published many papers. And one thing which I picked up here is their discovery that the heat transfer and through the walls and scanning of that is very important for accurate predictions. So on the right hand there, and they show the difference whether to consider that scaling or not when you consider different scales for your computation. And this, I now move to file separation and looking at some large-scale examples. And this is the work Zheng and his colleagues did some years ago. And the top, you have the 3-rack storage, comparing modeling, prediction with experiments, prediction experiments. So quantitatively, and both for the 3-layer and the 5-layer, and the simulation captured the experimentally observed scenarios. And more recently, again, it's Zheng and his colleagues, and they implemented the Dorofeev's frame extinction model and into file form, and this is a comparison with the experiments on the left. On the right hand here, and we have the work of White and all, and using FDS, again, looking at the extinction. And the important thing what they found was that when considering modeling flame extinction and those kind of scenario, and whether you consider reignition or not, it could significantly affect the results. So one needed to, for especially for underventilated scenarios, and both extinction and reignition needed to be considered, and that's also for better simulation of file separation. So a lot of challenges, and this is the earthquake and in 1921 in Japan. And after that, people discovered the serious situation was partly to do with the winning flame that was happened after the earthquake, and because the setup and the configurations of the regions, and you ended up have 3 types of firewalls. And conscious of time, I don't think I have time to go into details of that. So what we did is we implemented the vortex equation, and then looking at and to figure and to find out the mechanisms of different types of firewalls, and their link to barochronic Tokyo, and also to teaching and the transaction, and looking at the mechanisms behind the 3 types of firewalls. And moving quickly to emerging technologies, and my group has been working extensively in hydrogen and hydrogen safety. That's another community which has spent a lot of time. What you see here is a conventional hydrocarbon profile engulfing a high-pressure hydrogen tank. So in open form, we developed the conjugate heat transfer approach and dynamically coupling the fire dynamics will its attack on the tank. And we predict not only the tank temperature, but also the percentage of the virgin material that's left in the tank after the decomposition and following fire attack. And we also worked extensively on predicting jet files and hydrogen jet files, vertical, horizontal, or multiple jet files in tunnels. And more recently, we've been looking at cryogenic conditions and jet files. And typically, this could be anything from 20 to 120 K. And cold hydrogen jet files, hydrogen becomes liquid at 20 K. And so we were looking at, depending on the ignition point, if the ignition point is close to the release point, like in the top, or on the left here, half meter or 10 meter or 1 meter, and you get kind of diffusion flame surrounding surrounding at the edge of the jet, hydrogen jet. While in the center, it's really cold. It's cold, and flame is not propagating to the center and to the really cold center. But if the ignition point is 1.5 or 2 meter away from the release point, and we got a flammable mixture formed already, so you got a more partial premix flame, more dominated by premix combustion, but there are also diffusion flames on the edge. So it's very interesting. And another front which my team is working currently is battery failure and battery files. And my thinking is to do battery files, you always need to go back to the basics, why the file started. So we look at it the same wrong way, and what we did is, I don't believe in trying to do detailed simulations of what's happening with the battery inside all those reactions, because the materials change rapidly. So our approach is, when a new battery comes, and we test it in accelerating rate calorimeter. So we get these curves, and from those temperature curves, we fit one-step Arrhenius equations for different stages of the decomposition run-away process. And sometimes we compare the 2 stages, 3 stages, 5 stages, and then we put this in our CFD code, and so we can look at the thermal run-away situation of a single cell. And another reason of battery failure is mechanical damage. And in the experiment, it's typically, and it's captured with layer penetration. And these are the tests which are done, and the layer penetration test, which our partners in the project did. And we also developed our models to predict the evolution of surface temperature. We also have the internal temperature. You can see 3D, but I plotted the surface temperature here compared with experiments. So for axial penetration, and we can see our predictions agree well with one set of data, but not the others. A big reason is that people who did experiments told us it's difficult for them to get the layer just in through the really center. So every time they were testing, they were putting the layer penetrating in different locations. And while with the radial penetration, it's more easy for them to go through the middle, so we can see a better agreement with the data. And another important thing about batteries, and when they go into thermal runaway, and they don't just emit gases, the gases including hydrocarbons, as well as some percentage of hydrogen. But more importantly, there are also particles coming out. These are hot particles, and some of them are carbon, some of them are molten metals. And there's a big possibility that these solid particles and hot particles, they are actually the ignition sources of those combustible gases which come out. So in one of our project with industry, and we looked at the possibility of mitigating the propagation of thermal runaway and battery failure by putting some kind of special material. I can't say what material. Put some kind of special material, I would call it, on top of the cells, and that would have the effect that these particles come, and on the top there you have the cathode. So these battery are in modules, and on the top is a cathode. And the particles are reflected back, and if they fall right on the cell top, and it would easily trigger thermal runaway propagation. But if there's a material stopping, acting in between, and we would find that the chance of thermal runaway failure propagation would be significantly reduced. And we found that. I was commenting on Dong's paper on Tuesday. The gap between the top and between the casing and the cell top is also very important. And increasing this gap can help to prevent thermal runaway, at least to slow down it. But of course, for manufacturers, for industry, and even increasing 1 millimeter, sometimes it's a big problem for them. There's a spatial issues and the cost and weight, all sorts of things. So we also simulated the battery files. I don't think this looks like battery files, and I've showed you some photos which we did. But the thing what we are trying to do is we are trying to capture the global characteristics of battery files using simplified models, and which we derived, and these are jet files. They are driven by the pressure, the release pressure. So we actually did a measurement of the internal temperature, and we tried to measure the internal pressure as well, but unsuccessfully, because it's difficult to reseal after we put the pressure sensor in there. So we used the combination of internal temperature and the collected gas overpressure, and to derive a model which would give us approximately the pressure evolution inside the cell after thermal runaway, and used that as boundary conditions to model these files. And then we compared it with the cone calorimeter measurement of the heat release rate, which we got really good agreement. And so to conclude, and I think across the community, we've achieved file modeling has come a long way, and there are successes, but there are also great challenges. And I think a lack of detailed measurements for model validation, that's one of the problems we have. And upscaling, ideally, many of us writing proposals, we say we were going to do CFD modeling, then we are going to upscale from small scale validation to do large scale calculations. Sometimes it's not always the case, because even in small scale, we make some simplifications, and those simplifications don't necessarily hold when we go to large scale. And also, we are in a constantly changing world. Things are becoming complicated and need to be addressed. And also, not all researchers want to do models, especially to do something with lots of code development. Not all researchers want to do it. Every time when I recruit, sometimes I advertise 2 or 3 times interview until I find the right person to do the work, because otherwise I just couldn't get what I want to be done. And funding is a big issue, and fire and combustion, we are a traditional discipline, and I think research councils think that there's not that much science breakthrough you can achieve, and it's challenging. And in the UK, for example, it's almost impossible to get grants for files. I think my UK colleagues, if they're here, they would agree with me. But there are opportunities coming up, and there are many gaps with the emerging technologies, as well as code and standard. And it should be possible for more groups of file researchers to come together under some kind of international funding. So we do a bit of all this together. And also, there's a continuous increase in the cost of the larger scales. So that would in a sense, modelers can explore that situation and to benefit our research and get funding for it. So I would like to thank you all for listening. I would like to acknowledge all the researchers and who contributed to the work I quoted here. These are the modelers worked for me, or some are still working for me over the years, and our funding bodies, and these are all the names in the papers I quoted from the literature. So with that, I would like to thank you all again for listening. Thank you.